This is the formula to work out how much money you'll have when a bank pays a certain interest rate and you leave that money in the bank for a certain number of years. So for example, let's say the bank pays 4% interest. You start off with £1,000 and you leave that amount in the bank for 5 years. So you want to know how much money you'll have in the bank after 5 years. So what you do is just put the numbers in. P is going to be £1,000. R is the interest. It's a percentage, so it's going to be out of 100. I'm going to do this over a period of 5 years. I'll just round that to 2 decimal places. In a previous video, I showed you this in a slightly different way. Given this information, I showed you 1,000. We start with £1,000 multiplied by the interest is 4%, so we times by 1.04. If it was 5%, it'd be 1.05. If it was, let's say 30%, it'll be 1.30 or 1.3, and so on, over a period of 5 years. So you can see that. Remember, there's an invisible time sign there. So you've got the 1,000, you've got the times. 4 divided by 100 is 0.04. 0.04. 1 at 0.04 is 1.04. So all of that is 1.04 to the power of 5. So that's how I showed it. Right. The P stands for principal amount. It's what you start off with. R is the interest, and N is the number of times you'll be paid that interest. And in this case, I did it every 5 years. Right, let's say a hypothetical bank, a pretend bank, pays 100% interest. And you start off with £1. So the principal amount will be £1. So you write 1. The interest is 100%, so R is 100 out of 100 over a period of 1 year. So you want to know how much you'll get after 1 year, at the end of the first year. Now you could simplify this. You don't really need to put a 1 there, because you know, for example, in algebra, when you write 1x, you don't need the 1 there, do you? So we don't really need this 1 over here. Just assume there's a 1 there. You'll need that inside anyway. 100 divided by 100 is just 1. 1%, remember, 100% is worth 1 over a period of 1 year. So what will that be? 1 at 1 is 2. 2 to the power of 1 is 2. So you started off with £1 and you ended up with £2. So getting 100% interest is the same as doubling your money. Now what if the bank changes its rules? It's still 100% interest over a period of 1 year, but they want to do this, they want to spread this out, they want to pay you interest at the end of every month during that year. So you start off with £1, but I'm not going to put the 1 there. That 1 over here represents 100%, as I've just said. And that will be split up, divided by 12, because of the 12 months. And I want to know how much money I'll get after 12 months. You've got to understand this. At the bank, you start off with a certain amount, let's say £1. And then after, so that's the start. So after 1 month, the bank will give you interest, will pay you interest on that £1. You'll get a certain amount of money. And then the following month, 1 month later, the bank will pay you interest based on what you've just had a month ago. So you'll get a new amount there, and so on. The following month, So we're in March now, end of March. The bank will pay you interest on what was here, right, and that'll be the new amount. And this will carry on for 12 months. So that's what it is. £2.61. The bank will give you £2.61. I'll just write, okay, so that is fine. I'll just leave it as that now. Now the bank changes rules again. This time it wants to pay you every single day, at the end of every single day at midnight. So right, so we start off with £1, but I'm not going to write the 1. And then this is part of the formula. 100% is going to be divided by 365 because of 365 days. Right, some of you might be thinking 365.25 to consider leap year, but I'm not doing that. I'm just going to leave it as that. At the end of every single day for the whole year. Let's see what happens now. £2.71. Oh, you know what? It's going to get a little bit technical, so I'm just going to start writing a few more digits. All right. Let's take it a bit further. What if the bank wants to pay you every single hour throughout the year? So we need to figure out how many hours there are in a year. Well, there are 365 days in a year. Each day is 24 hours. That's how many hours there are in a year. Right, let's see what happens now. To the power of 8760. This is what I get. Almost the same as that. And so on. Right, the only similarity here so far is the 2.71, 2.71. Right, let's take this a bit further. Yes, let's do minute. Every minute the bank will pay you. So we need to figure out how many minutes there are. How many minutes there are in a year. Well, we got 8,760 hours in a year. We've established that already. Each hour is worth 60 minutes. That's how many minutes there are. Let's try that then. Right, still, it's the 2.71 that's common. And actually, it's a bit, I'm comparing this with this now. We've got as far as doing 2.718, 2.718, that's what's common so far. And I could take this even further, you know, do this here for seconds as well. If the bank pays you interest every second, that sounds a bit crazy, but we'll get an approximation of definitely 2.718 something, something, something. Right. That number here, it's got a special number. We'll represent it as E. That is the Euler's number, and the spelling is in the corner over here, if you can see there. Euler's number is approximately, this symbol here is approximately 2.718. Right. This number here, Euler's number, is a natural language for growth. As we've just seen, money's been growing. And that can be used, well, I will use for exponential graphs. I'm just going to sidetrack from this topic a little bit, and then I'll come back to this. You've heard of pi. Pi is a special number. And the formula for circumference, that's the distance all the way around, for any type of circle, circumference is equal to pi times diameter. Remember, diameter is that. So if you rearrange this to make pi the subject of the formula, c divided by d gives you pi. That means for any size circle, right, it could be a circle, a hypothetical circle as big as the universe. I don't know how big the universe is. No matter how small it is, could be the size of an atom, right? But when you do circumference divided by its diameter, any size circle, you'll always get pi 3.14 something something something, right? So pi can be obtained geometrically using shapes, whereas this one here, the Euler's number, cannot be obtained using geometry. Right? There is another special type of number. You know, when you try to do square root of a negative number, and you've probably done this in the past, you ended up with a maths error. Right, let's try this. Error. So how do we represent that mathematically? You're not going to say, oh, error, call that imaginary number, I. Represent that as I. Now there is an identity that links this Euler's number, the I and the pi. Here it is. It's an identity. Here it is. Right, you can represent angles in degrees or radians. So if you want to convert from degrees to radians, here's the formula. So for example, if you want to convert 180 degrees into radian, 180, just put the 180 in the formula. Now 180 and 180, they cancel out, you're left with just pi. So radian is equal to 180 degrees is equal to pi radians. Right. And likewise, if you want to change radians to degrees, and there's a formula for that. There is a formula that connects Euler's number E with trigonometry. Here it is. E, Euler's number, that's imaginary, and x is a variable. If I replace the x's with pi, remember that pi represents 180 degrees in radian form. So I'll do that then. Replace x with pi. Remember that's cos 180, same as cos 180, sine 180. Cos 180 is -1, sine 180 is 0. But you know 0 times anything is 0. So you're left with just that. I can bring that to the other side. Take that -1 to the other side, become +1. That's what you have. That's what I showed you just a while ago. This is Euler's identity, and so is this one. But the thing about this one is that it connects Euler's number with trigonometry. And that's got its uses in electrical engineering.